Hello, am I audible? Can anyone write in the chat box that you people are seeing my screen and I'm audible? Am I audible? Can anyone just write in chat box that I am audible? Okay. Thanks, Vita. So, okay. So, thank you. So, okay, so let me start. So, welcome you all to the problem solving session for the course of analytical chemistry, which is taken by Professor Devasis Ray. And I am Satya Prakash Yadav, PMRF scholar from August 2020 2020 batch. So, I am working with Professor Satish Patil in SSU Department of Indian Institute of Science, Bangalore. So this about the course. So in the week one, we have seen the chemical and material analysis method. Then in week two, we have seen the role of analytical chemistry and their techniques. In week three, we have seen the chemical equilibria and basis of the chemical analysis. And this from week four to week six, we are discussing the spectroscopic method. So here we are now. So in six we are now. So I am going to just briefly tell you that what all has been discussed in the this week six. So in the first lecture, 1 minute just. So in first lecture, then basically it's a continuation of the lecture 25. So there we have discussed about the analysis of the mixture. So basically, if we have the two mixtures, uh, how we can identify. So in the previous assignment, like we have solved like whether when we have this palladium 2 and gold 3. So how we can find out what is the concentration of palladium and gold via like Matthew Peregi. So that's the one thing in the lecture number 26. Then we have went to the photometric titration, where the reagent is the complexing agent, and then we just find out a species which is photometrically detectable, and then we have gone through like this like bismuth 3 plus and copper 2 plus estimation via EDTA using the photometric titration. So this is all about in 27 lecture. In 28, basically we have learned about the IR spectroscopy. So here we have see the instrumentation of the IR spectroscopy. Then we have gone through what are the fingerprint region and functional group region, what are the sources we are going to use, and how it is useful in the chemical analysis. Then in the lecture number 25, basically we have went through the FTIR. So the question come why there is a Fourier transform in the IR spectroscope, not in the FTUV. So basically here the professor has told about the uh, interferometer. So these are the interference pattern. So basically you have to uh, do the Fourier transform from time to the frequency domain. So that's why it's called the Fourier transform IR spectroscopy. Now in lecture number 13, basically we have seen the what happens once a molecule absorb uh, uh, electromagnetic radiation. So once it go to the excited state, what are all the possible processes happen and how it is helpful in the analysis, that we have discussed in the lecture number 30. So now I'm going to the assignment number 6. So basically the question is an analytical method in which radiant energy absorption of a solution is measured spectrophotometrically after each increment of the titration is added is called. Can anyone just write like what is the answer for the question number one? Then I will go and discuss detail what are the critical things we need to keep in mind. Can anyone write whether it is volumetric titration or conductometric titration or spectrophotometric titration or none of these? Anyone? Okay, so the saying C. All right. So Shweta is right. Like the option is the C. So the already the definition of the spectrophotometric titration is written in the question. So the first thing, what are the things we have to keep in mind? So the first thing is that at least one species one species should absorb the electromagnetic radiation. This is the basic condition for this spectrophotometric detectors. So if we have like one species which is absorbing the electromagnetic radiation, so we can monitor via incremental addition of the titer, right? So in this, while doing the experiment, you have to fix a wavelength. Basically, that lambda max for the species which is absorbing the electromagnetic radiation. So these are the two conditions. So suppose I am taking one example. So we have copper 2 plus and we are titrating with the EDTA in ammonia, right? So the species which is forming this is copper ammonium complex. This has a strong absorption around 745. So that once we record the spectra, we know that what is the lambda max for this copper ammonium complex. So now we are adding the EDTA. So what will happen? Now the most of the complex are EDTA are the colorless. Like basically the absorbance is decreased. So how the plot look like? So this is your absorbance and this is your volume of the titrate. Volume of the titrate, which is your EDT. So what will happen? So in the initial, it has the highest absorption. Once we are going to add the EDTA, so what will happen? The one more important thing is the formation constant. Formation constant, right? So this copper EDTA formation constant is greater than the copper ammonium complex. So basically, what will be remain in the solution? This copper EDTA. So what will happen? As we add EDTA, more and more copper EDTA will form, and the concentration of Cu like copper ammonium complex will decrease. So what will happen? Your absorbance will decrease. So what will happen like this? It will come like this. After the end point, it will be like no change. So this is one slope, that is the other slope, and this is your end point. So that's how like we know the end point. In the lecture, professor has already discussed about bismuth and copper. How the plots look like, you have already seen in the class. So now I will go to the next question. Next question is that a complexometric indicator which can be used in the titration for determination of a metal ion bounded by EDTA in solution is. Can anyone guess what is the answer for question number 2? Then I will go and discuss about that why that indicator is important. Okay, Shweta is saying the. Anyone else has any other like answer for this question? Okay, so anyone else don't have any other opinion. So the answer is right, ureochromic platinum. So now this EBT is very important because this this is important for the like water hardness determination. It is important for the metal and concentration detection. So this is very important indicator ureochromic platinum. So first we will see what is the ureochromic black tea. So it is like compound structure is this. I will just write and and there it is. Alright. Now this is the compound like structure for this ureochrom black tea. Now what happens if we have this is OH also here. pH CSO3 Na plus what about pH greater than 6, what is the change will happen? So what will happen? This OH will deprotonate and double bond in. So what will happen? This deprotonation will happen. And this deprotonated fat is in the color is blue. Now what happens if we add any metal? Suppose we have this magnesium 2 plus. It will form your magnesium EBT. EBT. Right? E plus H plus. So this color is your wine red color. Right? Now, one more important thing. What will happen if your pH is greater than 11.5? So what will happen? This is O minus, this is N double bond N. This is also red color. So the thing, if anyone has done the complexometric titration, they always say one thing that maintain the maintain the pH more or less around 10 by ammonia buffer. Here is the reason, because deprotonated farm, if we are deprotonating only one proton, it will be in blue color, and once it will form with the complex with the metal, it will give the wine red color. But if your pH will exceed 11.5, what will happen? It will be red. So wine red to wine red transition, you are not able to see that your endpoint. So this is very important. You have to maintain the pH for 10 by ammonia buffer in the complexometric titration once you are using iriochromate black. So the first thing is that this, if you have only one proton is deprotonated, it will be in blue color, and once it forms complex with the metal, it will give the one. This transition we need to detect the endpoint manually. So is it clear why we need buffer, like why we should maintain the pH 10 for the complexometric titration, and why iriochromate black tea is important? Because it will give the, like, in the deprotonated form it is blue. Once that metal, it will form your magnesium EBT compound. One more important thing, so what is happening is this your magnesium EBT complex is big compared to the EDTA. So what will happen? Your suppose you have EDTA. Once EDTA is present, it will be always in the magnesium EDTA. Once your EDTA get consumed, then magnesium EBT will form. Then you will see the violet color. So previously EBT will be in the uh, mono deprotonated form, but after the endpoint it will form a complex with the metal. So everything is clear. The three concept. What is pH? Other thing is the which one is for the Beaker complex. Which form is important for iriochromate black tea? So is all this concept clear? Can anyone just write that you have got the idea about this iriochromate black tea? Can anyone just write in the chat box? Then I will go to the next question. Is everything clear? Anyone can just write chat in chat box yes. Then I will go to the next question. Okay, thank you, Sweta. So next question, what is KBR used in the IR spectroscopy? It is the carrier for the sample, it is a detector, it is a source, or none of the above. Anyone can just write in the chat box. What is the answer for question number 3? Can anyone write in the chat box? Like what is the answer for question number 3? Whether it is A, B, C, or D. Okay. Surya is saying A. It is a carrier for the sample. Okay, Surya, can you write like why they are using KBR for the like carrier for the sample? Any property? Shweta is saying C. Okay, so let me explain. So, obviously, the identification of metal compound. No, this is not the correct answer. So, first thing, option A is correct. Sweta, option C is not correct because source already we have discussed. Whatever this near IR region, we are using the Nust blower source, which is basically your oxides of this yttrium. I think three oxides are there, and nichrome wire or global we can use, which is the silicon carbide rod. So these are the three source which through which we can do the IR spectrum. So source is not there. Basically, KBR we used as the sample preparation. So the palette preparation is very important, right? Very important. So what we do basically to record the spectra of solid and liquid, what we basically do, we take solid or liquid, very little amount of 2 to 3 mg, then we add 20 to 30 mg of KBR to make a pellet. To make a pellet. This pellet we just keep where sample holder is there. So now why we use this KBR? Because KBR is optically transparent. Optically transparent. Now the question, what does mean by optically transparent? It it does not have any absorption in the your IR region. So whatever IR region we are having, suppose this 500 centimeter inverse to 4000 centimeter inverse, it does not have any absorption in this region. That's why we are using the KBR. So whatever transmittance versus your wavelength or wave number we write, wave number, we are getting that some kind of this spectra, right? So this spectra we are getting somewhere. So this will come effectively from your sample, which is solid and liquid. It should not interfere by in what we are making, like KBR. So is it correct? Is it understood, Shweta, that why the answer is correct for this question number 3? Or you have any other question, you can write in the chat box. So the term we have to impart palette preparation in the in that preparation we have to use a optically transparent material. So that you have to know what does mean by this optically transparent and why we need it. Sweta, is it clear? Okay, yeah, thank you. Let me go to the next question. Next question: what is the color of ereochromic black tea in the deprotonated form? Now this I have already told. What is the color for the ereochromic black tea in the deprotonated form? Can anyone write in the chat box? Okay, yeah. Yeah. So that is right. It is the option number C. So we can go back. We can see that this is the ideochromic black tea. If pH is your greater than 6, this one proton will be taken by the this ionization of one proton will happen. This is in the blue in color. So that is the only will form a complex with the your uh, your uh, 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 your metal ion and which give a wine red color at the input. So yeah, Sweta, you have I think following the you are following the lectures. Great. So the option is C. So now question number 5 is what is the stretching frequency for carbonyl in aldehyde group in IR spectroscope? Anyone? Can anyone write for this question number answer for question number 5? What is the stretching frequency for carbonyl in the aldehyde group in IR spectroscopy? Okay, Surya is saying C. Okay, yeah. So yeah, so you are correct. So the carbonyl, if you have like ketone RCOR, another we have RCOH. So here basically your if you have aliphatic like uh, carbonyl group, so it will come from 1685 to 710 somewhere centimeter inverse, and this year will start from 720 to 740 centimeter inverse. So in the in IR spectroscopy, what you have to like think. So basically, you have to see the range where the functional group, like a functional group frequency came. So you have to categorize. You have to like somehow like remember. There is one sheet available in the BS Culture book. You can find out where it will. And other than that, once you are going for the analysis, then you have to be critically think what is the difference between those two compound which we can through which we can find out that this is the characteristic P which is responsible for that particular compound. So this is the way like how you have to see the IR spectra of any compound, and you have to like you have to rule out the other compound why that is not. So you have to see the particular frequency by which you can find out that what is that compound is. So basically this IR spectra is for the functional group detail. Okay. So I will go to the question number 6. So what is the range of the fingerprint region in the infrared spectroscope? That is again like so nice question. So can anyone write what is the range of fingerprint region in the infrared spectroscopy? Whether it is 4000 to 450 centimeter inverse or 1450 to 500 centimeter, 400 to 100 centimeter inverse, and none of them. Okay. Shweta is saying A, Soundarya is saying C. Oh. Anyone else? Okay, so this is also wrong. This is also wrong. So this is the correct answer for the fingerprint region. So why this is called fingerprint region? Because this region is unique like fingerprints. Sorry, fingerprints. So from 5,500 centimeter inverse, 40, 50 to 500 centimeter inverse, or roughly you can say 1500. So this is called fingerprint region. Fingerprint region. Okay, and from 450 to 4,000 centimeter inverse to, this is called functional group region. Functional group. These things you have to remember. Like in this, like your all the functional group will come in this region from 1500 to 4,000 centimeter inverse. Just give me. Okay. So this in IR spectroscopy, you people should, I think, already went ahead about this bending vibration and stretching vibration. So I will not go through that. Okay. So fingerprint region already this 500 centimeter inverse to 1500 centimeters inverse, and this is group frequency region or your functional group region. This is called group frequency region, which is from your 4,000 centimeter inverse to uh, 400. So basically in this region you are all keto or amine or alkene, amide, alkyne, and your OH and COH. This all the frequency will come in the group frequency region and functional group. Okay, so is it now it's clear like what is the fingerprint region in the this one group frequency region or functional group region? Shweta and Soundarya. Okay, thank you. So yeah, basically this your fingerprint region will be involving most of this all the bending vibration, which are low frequency region. So that is very hard to like define. So in your group frequency region, basically your stretching like stretching vibration will be there. Okay. So question number 7 is phosphorescence has a emission wavelength than fluorescence. So it is longer, shorter, or similar or undefined. Okay. So anyone has seen that lecture number 30, last lecture of the week 6, they can answer this question number 7. If you people tell, then I will go through the concepts. What are the concepts we have to keep in mind? This is photo physical processes. Can anyone just answer? Okay, Sweta is saying longer. Okay, Sandhya is saying shorter. Okay, okay. So let's see. So first of all, I will just plot the Jablonski diagram, which is very important. So suppose this is your ground state, singlet ground state. Then you have S1. This is first excited state. Then you have S2. Then you have S3. So this is the singlet ground state. This is your first singlet excited state, and then so on. Now we have the triplet state, which are lower in energy than your singlet state. Like that. So we have this first triplet excited state. So this is called T1, T2, T3. So now what are the processes happen? So what happens? So molecule will be always in the singlet ground state. So what will happen if we assign energy H? So what will happen? So it has different energy. So it will absorb and go to the S1, S2 and S3. So this is your absorption. On absorption, it will go to the higher excited state like S1, S2, S3. Now what will happen? So what can happen? It can come S2 to S3 to S2 via IC. I will tell what is IC. It can come from here to here via IC. IC is called internal conversion. Internal conversion. Okay. So what is internal conversion? Basically your SN to SN1 is one are through like this to S1. So what is happening? These are non-radiative. Non-radiative. So what will happen? Your molecule suppose went to the S3, so it will come to the S2 by releasing the heat. So the first thing is that it's not non-radiative, which it will not emit any radiation. Now, what it can happen? It can go through this way also. T1, S1 to T1, S1 to T1 are your SN to TN. These are called intersystem crossing. Intersystem crossing. Okay. So this is forbidden transition because here a spin is changing. So your singlet is like this, your triplet is on the both side. So this spin has to flip, right? So this is the forbidden transition, but it still it occur. Okay. So this is this is called intersystem crossing or ISC. Now what happens? One more process is there. Once it will come from S1 to S0. This is called fluorescence. Fluorescence. And other process is that it will come if it is come from T1 to S1. This is your called phosphorescence. Phosphorescence. What? Now tell me which one is having the higher energy, whether it is T1 to S0 or S1 to S0. So definitely your S1 to S0 has higher energy. Higher energy means this has lower energy. So lower energy means higher wavelength, right? So phosphorescence has higher or longer emission wavelength than the fluorescence. So this S1 to S0 and S1 to S0, these are the radiative transition. Radiative transition. So what do you mean by radiative transition? So it will emit a light with a certain specific wavelength. So these are called radiative transition. These are non-radiative transition because it will dissipate the heat and come back to the lower excited state. Okay. So the question is phosphorescence has longer emission wavelength than the fluorescence because we can see that these energy levels are like one more thing is that Tn will be always less than Sn. That is the things. Okay. Okay. No problem, sir. It's a only. Yeah. Okay, so now all the processes are clear. So all the processes are like, first is the absorption, second is the internal conversion, then we have intersystem crossing, then we have fluorescence and phosphorescence, all those things. So all the things are clear. Any doubt, then you can ask. Is everything clear? Anyone can just write in chat box that is clear for you. Yeah, thank you. So the thing is that you have to get the concept for all those things. Absorption, it will go to the excited state, that activated molecule, how it is coming to the ground state. And one more process is there, that vibrational relaxation, that I'm not going. Correct. Now the next question is, internal conversion is a radiative transition, radiative decay process, or non-radiative decay process, or absorptive, or cannot be explained. Can anyone just answer if they have understood the previous, like what concept I have told you? What is the answer for question number 8? Yeah, Sweta is C, B. Anyone else has different answer? So, yeah. So this is all the from higher excited state to lower excited state, whatever that transition is, that is called internal conversion, because here they will, the activated molecule will dissipate the heat, that is non-radiative. So all the transition is that are those are the non-radiative transition. So correct answer is B. Yeah, right. Okay. So next question. Anthracene source, option A is fluorescence and absorbance. V. Absorbance, no fluorescence. C. Fluorescence, no absorption. D. Neither absorbance nor fluorescence. Can anyone answer for this question? Anyone has answer for this question number 9? Anthracene source. Can anyone just write in chat box? What is the answer for question number 9? So anthracene is this molecule. 3-benzene ring. Anyone? What is the answer for question number 9? Oh, that is strange. No one has answered for question number 9. Okay, fine. So the anthracene has both your fluorescence and absorbance. So let me draw the this absorbance and this fluorescence spectra. So we'll be having like this. So this is your absorbance fluorescence intensity. So basically this is from 300 to 380 somewhere here. This is 460. So what is happening? It has both fluorescence and absorbance. So one important thing is here. The thing is that here you have to have the excited wavelength. Okay. Thing you have to get the concept what is the excited wavelength. Yeah, like you have to find out. So the where the maximum absorbance is there, that lambda max, you're basically the excited like excited wavelength. Then what the thing is that you have to give some width like 15 nanometer or whatever you nanometer, right? 15 nanometer, you have to give the offset. Suppose you excited at some wavelength called 375, then you have to start from 380. Why? Because you are giving a wavelength. So in the I think I can show you if I having molecule process here. So here basically you have two monochromator. So in one you are basically giving a wavelength that will excite your sample. Then whatever that one sample went to the excited state, then you are collecting what are the wavelength coming from them. So that if your excited wavelength, then the your recording wavelength will be same. Basically here you will get the maximum intensity. So to avoid that, we basically take the some offset of 15 nanometer, right? So the question is why enthranine. So first thing is that whether it will show the fluorescence or not, you have to like mostly whatever that conjugated like organic molecule will be there, they will show the fluorescence, right? But the thing whether it will show the fluorescence or not, you have to perform the experiment, then only we can say that whether it will show the fluorescence or not. Otherwise we have to do the DFT calculation, density functional theory. From there we have to see that how their excited state are, whether they are stable or not. Once your excited state are stable, it will come like it will be basically favor your transition like fluorescence or phosphorescence. So that's the way like we find out that whether it will show fluorescence or okay. So now question is that uh, okay, is it clear? Question number 9. Anyone can just write yes. Okay. Yeah. Thank you. So what is the device that measure fluorescence score? Thermometer, calorimeter, none of the above. This is a very simple question. Yeah, option C. Anyone else who can just say that no, now option C is not correct? Okay. So the answer is actually option C. So thermometer, basically here we measure the temperature. Calorimeter, basically we measure the heat. And fluorimeter, basically we measure the intensity, intensity versus wavelength. Right. So I will just go to that things here, fluorescence spectra. So these are things I have already told. What is the molecular radiation, whether it is non-radiative or fluorescence, like that. These things you can just go and see. This is, I think, most probably uh, uh, absorption and fluorescence intensity for this anthracene. This is your device. So basically, here what we first take a source, then we have the monochromator to give a single wavelength. Okay, where we excite it, where we get a single wavelength. That single wavelength will fall on the sample. Then that uh, uh, the sample will go to the your excited state, and once it went to the excited state, then basically we have the emission spectrometer, where we just record what are the wavelength and what is their intensity. So we basically count through the transducer, and there is a readout device. So basically we get a intensity versus wavelength, plot, like something like this. Okay. Okay. One question can I ask? Why this peak? Some peak are coming like up, then it is going down. So it will be, if you see, so it will be like something like this. Always in the this is your fluorescence. In this one, it will be like this. That you people should go and see why the spectra looks like this. Higher energy or okay. So I will share this PPT with you, that whatever that link is there. Okay. If anyone has any question, they can ask now. Otherwise, thank you all for joining. Okay. So now I will just sign out. Anyone has any question? Okay. Okay. Then thank you all. So I will just sign out. Mhm.